Welcome back to our ongoing deep dive into the OEIS. Today we're tackling a sequence you, our listener, specifically requested, A000099.
Ah, yes, ever 000099.
Get ready to explore the Gauss circle problem.
It's a deceptively simple problem that has captivated mathematicians for centuries.
Okay.
Imagine a circle on a grid centered at the origin.
Okay, got it.
The question is, how many points with integer coordinates or lattice points fall inside that circle?
So A000099 basically just lists those counts as the circle's radius grows, right?
Precisely.
I checked it out, and the first few terms are 1, 5, 13, 29. It's like we're literally building out circles on graph paper and tallying up the dots.
But the beauty lies in what this simple act of counting reveals.
What's that?
It turns out this problem is deeply connected to approximating the area of a circle.
Interesting.
Think of the unit squares on our grid. We're using them to estimate the circle's area, but there's always a bit of error involved.
Because those square blocks don't fit perfectly into the curved shape of the circle.
Yeah,
so the Gauss circle problem is about quantifying that error.
Exactly. It seeks to understand the difference between the actual number of lattice points in the circle and the theoretical area given by Verse.
Okay.
And mathematicians have been trying to pin down just how big that error can get.
I read that Gauss himself made some headway on this, right?
He did. Gauss established an upper bound for the error term, showing that it couldn't grow too wildly. Later, Hardy and Landau, working independently, found a lower bound,
Interesting.
using that little O notation to describe its behavior.
Okay, I have to admit, I always get a little tripped up by that notation.
Oh, really?
Could you refresh my memory on what it signifies?
Certainly. In this context, the little O notation tells us that the error term grows slower than a certain function.
Right.
Hardy and Landau showed it couldn't be too small, even though the exact growth rate remained a mystery.
So where do things stand now? Have mathematicians managed to close in on the true nature of that error term?
There's a prevailing conjecture that suggests the error term is bounded by a function with an exponent slightly larger than 12.
Okay.
Finding the exact value of that exponent is a major open problem, with Huxley's work giving us the best upper bound we have so far.
So we have this kind of squeeze happening with upper and lower bounds getting closer and closer to the true behavior of the error term.
Precisely.
Fascinating.
And the pursuit of that true bound is where things get even more intriguing.
Really?
We have exact formulas for NR, the number of lattice points, some involving series with floor functions, others connecting the problem to Jacobi's two-square theorem, and the ways to represent an integer as the sum of two squares.
Wait, hold on.
Sure.
I vaguely remember the floor function, but a quick refresher would be great.
Of course. The floor function simply gives you the largest integer less than or equal to a given number. It's a way to chop off the decimal part and deal with whole numbers.
Right.
Which is crucial when we're counting lattice points.
Okay, that makes sense.
So we've got these different ways to express the number of lattice points.
Yeah.
Some involving clever mathematical tools like the floor function.
But how does all of this connect back to the error term and its elusive bound?
That's where the deeper analysis comes in.
Okay.
By carefully manipulating and approximating these formulas, mathematicians try to gain a better understanding of how the error term behaves as the radius of our circle expands.
And this is where techniques from analysis and number theory come into play, right?
Yeah, absolutely.
I even saw something about Bessel functions in our sources.
Hardy, for instance, developed an identity using Bessel functions to represent NR.
Wow.
It highlights the fascinating and often unexpected connections between seemingly disparate areas of mathematics.
So we've got this interplay between the visual geometric idea of counting points in a circle and the abstract analytical world of formulas and approximations.
Yes.
It's like those two sides are constantly informing and enriching each other. Feels like we've only scratched the surface here.
Well, yeah.
Our source material mentions generalizing this problem to higher dimensions.
Yes.
What does that even look like?
Imagine moving beyond our flat two-dimensional grid.
Okay.
Instead of a circle, we now have a hypersphere. A sphere in a space with more than 3 dimensions.
Okay.
It's hard to visualize.
Yeah, I can imagine.
But the core question remains the same. How many lattice points fall within this higher dimensional sphere?
Okay, I can vaguely grasp the concept, but the notation gets a little intimidating.
Really?
Our sources use terms like LKX, AKX, VKX, and PKX.
Oh, right.
Could you break those down for me?
Of course. LKX represents the actual set of lattice points within a k-dimensional hypersphere.
Okay.
AKX counts the number of those points.
Got it.
pkx gives us the volume of that hypersphere,
Right.
the higher dimensional equivalent of area.
Right.
And pkx, our old friend the error term, represent the difference between the point count and the theoretical volume.
So it's basically the same idea as the circle, just extended to these abstract, higher dimensional shapes.
Right.
But I imagine things get a lot more complex, right?
They do. We still have some general results, like
Right.
those from Wolfus,
Okay.
giving us bounds on the error term. But pinpointing the greatest lower bound, denoted as BIC, becomes a real challenge.
I see.
Each dimension seems to have its own unique quirks.
It's amazing how mathematicians even begin to tackle these problems.
Oh, I know, right?
Our sources mention things like recursive relations and exploiting symmetries to calculate x.
Yeah.
It sounds incredibly intricate.
It is. Imagine trying to calculate the number of lattice points within a four-dimensional sphere.
Wow.
It quickly becomes computationally demanding.
Right.
But by using clever techniques, mathematicians can leverage patterns and structures to make those calculations more manageable.
Our sources also mention some interesting findings from numerical studies.
Oh.
They talk about analyzing extreme points and how their distribution relates to the error term, bounds. It seems like those numerical experiments provide valuable insights.
Absolutely. Researchers like W.C. Mitchell, whose work we're examining, have used computational methods to analyze these higher dimensional cases. By looking at patterns in the distribution of lattice points, they can formulate conjectures about the behavior of DAC for different dimensions.
For instance, they suggest that day 2, the lower bound for the two-dimensional case, is around 0.324.
Yeah.
Which, intriguingly, happens to be very close to 1237.
Right.
It makes you wonder if there's some deeper connection there.
It's those kinds of numerical observations that often spark new avenues of investigation.
Yeah, that makes sense.
It's like finding a clue that hints at a hidden pattern or underlying structure.
And then there's the whole issue of the sign of pkx, the error term.
Yes.
I was surprised to learn that for a circle, it tends to be negative most of the time.
Oh.
Why is that?
It's a curious phenomenon, and there are various explanations based on geometric and analytical arguments. In essence, the distribution of lattice points often skews slightly towards the inside of the circle, leading to a negative error term.
I see.
But in higher dimensions, that sign behavior becomes less predictable.
So we have this unexpected twist where even the sign of the error term adds another layer of complexity to the problem.
Precisely. And that's part of what makes the Gauss circle problem and its generalizations so fascinating.
Yeah.
It starts with a simple question.
Right.
But as we dig deeper, we uncover a rich tapestry of mathematical connections and unexpected behaviors.
We focus so much on circles and spheres.
Right.
What about other shapes? Does this whole lattice point idea apply to them too?
It absolutely does.
Really?
Our sources even touch on Dirichlet's divisor problem, which looks at lattice points under a hyperbola instead of inside a circle.
Interesting.
Mathematicians have investigated this kind of question for squares, triangles, you name it.
Wow.
It's a whole field of study.
So A000099, while focused on the circle, is like a gateway to a much broader class of problems in geometric number theory.
Precisely.
Okay, cool.
The techniques we've been discussing, finding bounds, using series, exploring higher dimensions, these are fundamental tools for understanding the interplay between geometry and number theory.
Speaking of other shapes, I'm curious about something mentioned in our n-sphere source.
What's that?
The octahedral sphere.
Right.
This sounds like a strange mix.
It's a fascinating concept.
What is it?
An octahedral sphere is defined much like a regular n-sphere, but instead of our usual Euclidean distance, it uses what's called the one norm or taxicab distance.
Okay, remind me how taxicab distance works again.
Imagine you're in a city where you can only travel along the grid streets.
Okay.
Taxicab distance measures how far you'd have to drive to get from one point to another, always following those grid lines.
So no cutting across blocks diagonally.
Exactly.
So an octahedral sphere using that distance wouldn't look like a smooth round sphere?
Exactly. It would have flat faces and sharp corners.
Wow.
In fact, it ends up looking like a cross polytope.
Okay.
A generalization of an octahedron to higher dimensions.
I see.
It shows how changing the distance metric can drastically change the shape we're studying.
So after this deep dive into A000099 and the Gauss circle problem, what stands out to you the most?
What amazes me is how such a simple question, how many points in a circle, opens up this vast and intricate mathematical landscape.
Right.
We've touched on geometry, number theory, analysis, even topology, all stemming from this one problem.
And even after centuries of study, there are still open questions and conjectures to explore. It really highlights the dynamic and ever-evolving nature of mathematics.
Absolutely.
Well, this deep dive has given me a taste of the depth and beauty of the gas circle problem and its connections.
It has.
Yeah. Hopefully it inspires our listeners to keep exploring the fascinating world of number theory and the many mysteries it holds.
That would be great.
We've seen how counting points in a circle leads to complex questions with implications in higher dimensions.
We have.
But what if we did change the shape, as we discussed? Could we apply similar techniques to other geometric objects? It's a question worth pondering as you continue your mathematical journey.
Definitely.
Thanks for joining us on this deep dive into A000099.